Visible to everyone? Can anyone unmute and just tell me?
Yes, sir.
Okay.
Yes, sir. Yes, sir.
Okay. Thank you. So, good evening, everyone. Welcome to the first live session for the course Advanced Reinforced Concrete Design offered by NPTEL. I am Harshit Agrawal, a PMRF research scholar from the Department of Civil Engineering, IIT Bombay, and I will be taking weekly live session for this course for the entire course duration. So first of all, what are these doubt clearing and interactive session all about? So these are weekly interactive sessions that will be taken by me every Tuesday from 6 p.m. to 8 p.m. till the course runs. So that is for 12 weeks. Um, in during these sessions, we will interact by answering to my questions that I will ask in the chat box, by posting your questions in the chat box, or by raising hand, unmuting, and asking your queries. Apart from the class, you can always use the discussion forum of the course where you can post your queries and the answers will be addressed to you either through the discussion forum itself or in the next live session probably. And if you will attend these sessions regularly, it will help you to answer the graded assignments easily, and it will help you to further understand complex topics holistically. So in today's session, we'll first have an overview of the course just to familiarize everyone what this course will be offering to the learners. Then we'll see how module of this course is divided into 12-week content. Starting with week 1, we'll first have a basic overview of concrete as a construction material. We'll talk about different components of a concrete and how concrete act as a composite. Then we'll start the main discussion part where we'll start discussing about reinforced concrete, its history, why it is needed, and different components of a building or a structure that is made with reinforced concrete. And finally, we'll talk a little bit about design of reinforced concrete, different codes of design, and different design methods. So the theoretical part that we will be discussing today would be a just quick recap of week's content, where if anyone has any doubt, they can ask their queries. Along with the theory, in between, I will introduce you with some questions to challenge your understanding of the subject. In total, there will be around 11 to 12 questions that we'll discuss today. And in the end, at the end, I will make myself available to solve any other queries related to the assignment questions. So I just advise everyone to attend these sessions regularly, so as it will help you to gain thorough understanding of the course. If something you are not able to understand in the recorded session, you can clarify it here during the live session. For coming weeks, we will have more questions to discuss, assignments as well as extra question. So quick theory recap plus questions will provide everyone proper clarity of concept. So I hope everyone are clear with the flow of the session. Whenever anyone has any doubt, you can just type in the chat box, and in between when I will stop for discussing questions, during that time I will see your queries in the chat box, or I will allow you to unmute and ask your queries. Okay, so let's start. So this course is for in-depth understanding about advanced concepts of reinforced concrete design. Okay, where we will learn analysis and design of advanced or complex structure elements you based on coded guidelines and practices. Okay, so in this course there are four basic parts as you can see. Okay. Uh, Basics of reinforced concrete design is the first part, which will include discussion on cement type, strength gain, and different types of concrete, stress strain distribution, behavior of concrete and steel. So, this will be the first part of the course. Then, durability side of reinforced concrete will come, where we talk about different degradation or deterioration mechanisms and their remedial strategies, and how design of our reinforced concrete takes cares about these degradation mechanisms. Then we'll discuss about behavior of reinforced concrete under axial flexure, shear and torsion. And finally, we'll explore various aspects of reinforced concrete design for columns and slabs and different serviceability criteria that are assigned during the design. So week one, we'll start with overview of reinforced concrete and design philosophies, and we will end with week 12 with the discussion on analysis and design of reinforced concrete slab members. Okay, so this is the flow of the course. So here you can see the course is divided into 12 modules, starting with week 1 where we are talking about introduction to reinforced concrete design. In week 2 we'll come to materials and properties of reinforced concrete system. Third week we'll talk about durability of reinforced concrete. Then fourth week we'll start with the design part. So fourth week will be about axial design. Then week 5 and week 6 will be more related to the flexure design of reinforced concrete. Week 7 will come to shear design. Week 8 will talk about torsion. And week 9 we'll talk about our analysis and design of reinforced concrete column in week 9 and week 10 both. Okay. Then we'll talk about serviceability checks in the reinforced concrete design, and finally we'll end with analysis and design of two-way slabs. Okay. So let's start with the week 1. Okay, so we are all well versed with the fact that in the present world, concrete is the most widely used construction material. Okay, and facts supports this statement, as we can see it is the second most consumed material on earth after water, and more than 5 million tons of concrete is consumed everywhere. Okay. Now the point is what makes concrete so special? Why we are using concrete? It is because of its five key characteristics. First is the behavior. It can act as a barrier against, like it can provide excellent water resistance property. Its strength, it can withstand load. Affordability, it is a easily available raw material and it is cheaper compared to steel. Durability, it has a significantly high lifespan which makes it durable. And flexibility, we can mold concrete into any desired shape and size based on our requirement. So these special properties of concrete makes it so special and so widely used as construction material. Now, how we define concrete, like what is concrete? So if we write it as a formula, we can say concrete is equal to binding material plus water plus fine and coarse aggregate plus admixtures. So in layman term, if I say concrete is a material which is flowable, which is a kind of a slurry, a flowable slurry at the initial mix, but over time it hardens and sets and becomes a definite stone like mass which can resist load. Okay. Now, if we see different components of concrete, like what are the role of each of these component in making concrete, you see binding material is the main element of a concrete mixture. And by binding material, we use cement as the most commonly used binding material. So what happens? This cement, it combines with water, which provides workability to my concrete to make a paste which hardens and gives concrete its strength. Okay. Then this coarse aggregate and fine aggregates, these are inert materials that are there in concrete. So by fine aggregate, we generally mean sand, which act as a fine mixture, which acts as a filler in my concrete system. And coarse aggregate are generally gravels and crushed stone, and they combine provide the dimensional stability to concrete. What do we mean by dimensional stability? We'll understand when in the coming weeks or in the discussion ahead we will understand this reaction of how paste is formed and why dimensional stability is needed. That will be clear at that time. Or if you are well aware with the basics of concrete, you know why dimensional stability is there required in the concrete. And the last element are the admixtures, which include chemical and mineral admixture that are added as an additional part or as a replacement, and they are used to enhance the performance or the durability of concrete. Okay, and all these combine to make a stone-like substance, which we call as concrete. So the illustration of this formula you can see in the images here. So the first image shows a flowable slurry kind of material that is produced after initial mixing of all these components. Okay, and the second figure shows the what happens over time, how concrete hardens and it sets into a definite stone like mass which we use for construction activity. Now, if we look at the history of concrete material, so the history of concrete begins in 1800 with John Smitten, who is credited with developing the first modern concrete using hydraulic lime, and he used this concrete for building a durable structure like Eddystone Lighthouse during that time. Okay. Then in 1824, Joseph Espedin patented Portland cement, which was a revolutionary movement in construction industry. So then in 1867, Joseph Monier introduced reinforced concrete by combining steel and cement. In 1892, Hibinic again worked in advance with reinforced concrete and used it in a structural construction that we'll see soon in the next slide. In 1933, Freyssinet, a scientist, developed pre-stressed concrete to resist tensile forces, and then innovation continued further with FRP, fiber reinforced polymer, coming into picture in 1957. Then high performance concrete was introduced in 1970. Ultra high performance concrete came in 1994, and at the most recent advancement is the pre-stressed concrete combined with FRP tendons that started in 2020. However, if we specifically look at reinforced concrete, so the Hibinic system was the one of the first appearance of modern reinforced concrete system. Okay, the first building was erected in United Kingdom using this system, and it was the Weaver Building in 1897. So what he beneath the he this person he began with reinforced concrete floor slab in 1897, and he progressed to complete a complete building system which was patented in 1892. And why we say it as modern? Because the complete building was composed of structural reinforced concrete design, which included stirrups and longitudinal rebar, as you can see in the image. So you can see there are longitudinal bars also and stirrups also, just like how we use in present time. Okay, so that's why we say this was a kind of beginning of a reinforced concrete design. Now, why we require reinforcement, like why we are emphasizing so much on reinforced concrete? So if we see, concrete is a brittle material. It is good in compression but very weak in tension. So in actual application, there are both compressive load and bending or tensile load that acts on a structure. So if there is just concrete, it will crack easily in the tension zone. So we know this is neutral axis. Above this, there is compression zone. Below this, there is tension zone. Since concrete is very weak in tension, it will crack easily in the tension zone. Therefore, to make concrete strong in tension, what we do, we embed steel reinforcement inside concrete, which has high tensile strength. So, what reinforcement does? It prevents crack from propagating, and it takes the tensile load until it heals. Okay, so this makes concrete, a reinforced concrete, good in compression as well as in tension. So you can see here, concrete takes the compressive load and steel takes the tensile load, and both these material act as a composite in the construction application. In this slide, you can see a wide range of application of reinforced concrete as a construction material in India. So the first figure shows you the use of reinforced concrete in metro lines for decks and piers. Okay, this is one of the photo of Delhi metro line. In the second figure shows the use of reinforced concrete in dams. So this image is specifically taken of Metupati Dam in Kerala. In the third figure, you can see the use of reinforced concrete in high-rise buildings, like the one uh, shown here is from some outskirt areas of Delhi. And in the fourth image shows the use of reinforced concrete design in bridge construction. One of the most famous examples, as shown in this figure, is the Bandra Worli ceiling in Mumbai. So this shows that reinforced concrete has a wide range of applications as a construction material. So till now it was just basics, like not much questions should come here in the basics part, but still I will try to ask you some questions here to just check your clarity about the basics. So these are three questions. Kindly think about these questions, and if you know the answer, type in the chat box which will be the correct option, and then we'll discuss. And if anyone has any doubt in the session till now, they can also ask that. I will unmute myself for a couple of minutes so that you can think about the questions and their answer, and then we'll discuss. Okay, let's discuss the answers now. So the first question is, which of the following properties of steel it makes it ideal for user reinforcement in concrete? So the correct answer for this is D. Okay, so we know that steel has high tensile strength, but the key reason why it is ideal for reinforcement is its similar thermal expansion coefficient as compared to concrete. Now, why this is important? Because this ensures that both materials are both materials expand and contract at nearly the same rate under temperature fluctuation, and this prevents any internal stress or cracking to happen due to fluctuation in temperature. So that's why steel is ideal is mainly due to the similar coefficient of thermal expansion. Question number 2: which of the following is not an advantage of reinforced concrete over structural steel? So the correct answer for this will be C, greater ductility. Okay, why? So we know reinforced concrete offers many advantages like better fire resistance, uh, a lower maintenance due to composite behavior or monolithic behavior to act as a single unit. However, we can't say directly greater ductility because structural steel, which are also used in construction, which are purely made of steel, is more ductile. That means it can undergo more deformation before failure. However, in contrast, concrete is brittle and unless it is combined with the ductile reinforcement. So it is not like a direct advantage of reinforced concrete. Other are some of the more advantageous things about reinforced concrete. Okay. And question number 3: what is the main factor of function of transfer reinforcement in reinforced concrete beam? So if you know have a little clarity about design of reinforced concrete, so you will know that stirrups that we use, they are primarily used to resist shear force, or we can say any kind of diagonal tensile force that develop near supports or near loading points, especially in beams. Okay, so in columns they confine concrete in compression, and they enhance the ductility and load carrying capacity of concrete. Okay, so if we generally see stirrups as a secondary role in overall strength of reinforced concrete, but their presence is also very vital in preventing any kind of shear failure or for maintaining the integrity of concrete. Okay, so that's why the correct answer will be C. Okay, any doubts in these three questions? I guess these were very basic questions. Okay, see, stirrups if you know, there are two types of member: horizontal member and vertical members. So in horizontal member, there are shear failures that generally associate near the supports. So what stirrups do, they provide that resistance, the diagonal resistance, the resistance against diagonal failures that can occur in a beam kind of thing. So their stirrups helps a beam, a reinforced concrete beam, to resist any kind of shear failures. While in column, it is providing that confinement. It is keeping the reinforcement, the longitudinal reinforcement, in their original position, and it is it is confining the concrete in the compression zone, which enhances the ductility of concrete. Over time, when we'll talk about design, it will be more clear. It will become clearer how stirrups are playing role. But for now, you can just understand they are also a very important part in resisting any kind of shear or diagonal forces that act on a reinforced concrete structure. Okay, okay, let's move ahead then. Now, when we talk about a reinforced concrete structure, there are different components, or we can say different members in a reinforced concrete, and all these members combine together to make a complete reinforced concrete structure. So if we just visualize these components, we have footings. Okay, so we have footings which form the base of any construction project, which connects our above ground level part of reinforced concrete to below ground level for transferring the load to the subsoil. And then there is tie beams, which lay the base over the ground. Okay, and there are columns which are the vertical reinforced concrete member responsible for elevating a reinforced concrete to different heights. There are beams which lay the base for each floor of a reinforced concrete. And finally, there is slabs. There are slabs, which is basically the floor of a reinforced concrete structure and the first point of contact where loads act on a reinforced concrete. So these are like basic components of reinforced concrete, which over time in this course we'll discuss in detail in design. Now, from design point of view, if we see, we first design slab, then load comes to beam, then beam is designed, and then we design for column, and finally we design for footing. So the design philosophy follows a top to bottom approach. However, while implementation or while during construction, it is the opposite of design. We first first footings are laid, then columns are made, then beams, and then slabs. So therefore, we say construction philosophy follows a bottom to top approach, and both these approach are opposite to each other. Design is done from top to bottom based on how the load is getting distributed everywhere, and construction starts from bottom to top. Okay. Now, why this design thing is important, like why we are focusing so much on design, so we can understand this from this evolution of building design with increasing height, like how you saw in the NPTEL session. So for low rise buildings, like for 1 to 3 floor buildings, the key structure elements are slabs, beams, columns, and footing, because there is only basic gravity loads and live loads that are acting on the building. However, if we go to mid-rise level, if we increase the height of the building to 4 to 10 floors, what will happen? Apart from these basic elements, shear walls and moment resisting frames will also come into design to resist the lateral forces that is acting on the building due to wind or seismic activities. Now, if we go further to high rise level, that is 10 plus floors, there will be core walls, outriggers, and transfer girders that comes into design to enhance the control over any kind of drift or torsion or overturning in the building. And then in skyscrapers like Burj Khalifa, the structure is a bundled tube structure. So if you see, structure is like this, a bundled tube. Okay, there is a big building in the center and small buildings on the side. So it is a bundled tube structure with mega columns and diagrids, as we say. And these are some advanced design that is used to provide uh, high control over seismics and wind loads activities. Okay, so that's why design is important. It helps us to make reinforced concrete safe as per condition and as per requirement. Now, there are four key objectives of reinforced concrete design. Okay, what are these objectives? First is strength, which resist safely the stresses induced by loads and various structural elements. Then there is stability to prevent any kind of overturning, sliding, or buckling of structure. There is serviceability to ensure that performance of my building is satisfactory over time, and this durability to ensure that the service life of my building or my RC structure is maintained even in aggressive conditions. Okay, so to achieve these four key objectives, design is needed. And along with these four key objectives, other decision elements are also involved in design, like functional and safety considerations during operation, physical and economic constraints of the projects, uh, the overview or out outlook of stakeholders and agencies that are involved in the projects, and the process and the requirements of construction. All these minor things also combine together to finalize design of a reinforced concrete structure. Now, to ensure uniformity and safety in construction, we need a common language in design, and that's where design codes come into play. Okay, so this slide shows you IS 456, which is the fundamental code for reinforced concrete design in India, and it has five key sections and eight annexes. So first section is about general materials, second is about material workmanship inspection testing, then there's the section third which talks about design consideration, section four which talks about special design requirement, and section five which talks about limit state method. Okay, so every structural engineer refers to this code for basic rule of reinforced concrete design and detailing. Strength, however, strength doesn't come from design. It also comes from quality of material. Like, strength is not just about design. It also the material that we are using also plays an important role in that. So that's why we have IS 10262, which guides us how the proportioning of concrete ingredients should be done to achieve a desired strength, workability, and durability. Okay, so this section again has five sections which are divided into different knowledge of understanding of our about concrete mix proportioning, and what all deviations can come on site, and some examples of how mix proportioning can be done. And from selecting the target mean strength to achieving how much water to use, how much cement to use, and how much aggregate to use, this code ensures that our concrete performs as per our intended purpose. Beyond material and structural design, we also need to consider loads acting on structure. So IS 875, it estimates the various loads on the structure like dead load, live load, wind load, and snow load. While IS 8 1893 and IS 39 139260, these are codal guidelines for earthquake resistance design. And to ease practical design work, we also have SP34 and SP16, which provide design charts and detailed guidelines for implementing design codes in reinforced concrete design. Okay, so just to summarize what these design codes are doing, they are providing standardization to us so that whatever mixture proportions we are choosing or whatever design we are making, it is consistent, and it provides a unified approach for engineers across the country. It provides guidelines on material properties, like standardized value for concrete and steel durability parameters and other essential material characteristics. It guides us for load and load combination, which helps us to define what all loads can act on a system. It provides us the serviceability criteria so that we can limit the deflection, cracking, and vibration in our system. It provides us the durability requirements, which helps us to ensure that our structure performs well over time also. It provides us the legal or regulatory compliance, like following codes is often mandatory by law and local authorities for approval and certification of the structure. Okay, it provides us that common language of design, and it acts as a basis for quality control and inspection. So suppose you have done a reinforced concrete design and someone is checking whether your design is proper or not. So design codes provides us the benchmark for people to judge whether the design is done properly or not. And if there is some problem in the structure, then also design codes helps us to find what is the problem in the proportioning or in the material. Okay, now try to answer these three questions based on the discussion on design. In the meantime, if you have any doubts, you can ask. uh, I guess there was some connection disturbance in the middle. Were you able to see my lecture? Okay, okay, just try to answer these three questions. Okay, let's see the answers now. So question number 4, the ultimate goal of reinforced concrete design is to. So the correct answer will be C for this. Okay. So when we are talking about reinforced concrete design, it is not just about strength of concrete or entire composite material. There are three aims of design. My structure should be safe, it should not collapse. My structure should be serviceable, like there should not be excessive deflection or cracking in the structure, and the design should be economical. Okay, so what these design code does, they provide practices that can enforce a balanced approach for achieving all these three criteria. Okay. Fifth question, in context of design codes, what distinguishes IS 456 from IS 10262? Okay, so again, the correct answer will be C for this. Okay. So IS 456 is the main code for reinforced concrete design. It covers the basics of structural design, durability, detailing, and loads, while IS 10262 focuses more on the mixture design of concrete, which helps us to determine the proportion of cement, sand, aggregate, water, and admixtures that we need to achieve a desired concrete grade. So this is the base code, and this is a supplementary code specifically for concrete mixture proportion. Okay. Question number 6. Which of the following statement correctly distinguishes IS 456 and IS 13920? Okay. So the correct answer for this will be B. Okay. So IS 456 is again a guideline for design and construction of reinforced concrete in normal condition. However, in seismic zones, IS 19320 is used to provide additional detailing or ductile detailing requirements to enhance the energy dissipation and prevent any brittle failure during earthquake. So we design a building by IS 456, and then if the building is in seismic risk zone, we need to follow the guidelines of IS 13920 also to check whether our design is safe for earthquake activities or not. And if not, IS 13920 provides us the additional rules or additional requirements that should be imposed in the structure to make it safe for from earthquake damages. Okay. Any doubt in these things? Any doubt in these three questions? Okay, so let's continue ahead then. Now, based on the proportioning of various ingredients that we use in concreting and various types of admixtures that we are using, concrete can be classified into different types. So, like there is regular concrete, there is reinforced concrete, there is pre-stressed concrete, there is high strength concrete, high performance concrete, self consolidating concrete, shotcrete, roller compacted concrete, glass concrete, asphalt concrete, rapid strength concrete, and polymer concrete. So among the as per now, there are 23 different types of concrete that are listed that I found in this source, and among these, the most commonly used are the first three: regular concrete, reinforced concrete, and pre-stressed concrete. So plain concrete and reinforced concrete, we have already seen the difference. It is just the additional reinforcement that is coming in reinforced concrete. However, unlike reinforced concrete, pre-stressed concrete uses tension steel strands to apply compressive force on concrete to improve its strength and crack resistance. So, in the left image, you can see there are multiple strands of post-tensioning systems that are present inside a reinforced concrete beam. Okay, and in the in the right image, you can see how it compares with the normal reinforced concrete. So if you see a normal reinforced concrete under load, what will happen? It will crack in the tension zone, and steel will be resisting this crack from growing completely. However, in post tensioning, what happens before loading? It gives a compressive force to the concrete, and this makes concrete not to crack after load is applied. Okay, so this is the basis of pre-stress. It won't crack under loading, okay, due to the pre-applied compression by the post tensions. Okay. Now, coming to the last segment of this session, we will see what is the difference between design and analysis. So, okay, so this slide just compares design and analysis of reinforced concrete. So, what we mean by design? So, design means determination of type of structural system to be used, the span, the cross sectional dimension, and the required reinforcement area and dimension. So, during design, what we know the grade of our material, what grade I'm using, M20, M25, M40, whatever grade of concrete I'm using, I may have that knowledge. I may have the knowledge about the steel quality also, whether it is Fe415, Fe550, Fe500, whatever grade of steel I have in my inventory I have. And from the structural design, I know what is the bending moment acting on my structure. Knowing these basic things, I will design a reinforced concrete for the shape, the dimension, and the requirement of the material, like width and the height and the reinforcement area required. Okay, so this is design. So design ensures that the detailing given to the structure will be capable to resist all the forces and the moment acting on the structure during its lifeline within acceptable deformation or cracking limits. So this is the role of design. We know what is the load acting on the material and what is the quality of our material, and we are determining the dimension and the amount of material that we need. And what this analysis does, analysis is the determination of yes, hello, your voice is breaking. Just type in the chat box, I will read from there and then answer. Just let me complete what this analysis is and then we'll discuss. Okay, so analysis is the determination of capacity of a section if we know the dimension, material properties, and the concrete specification. So it is just the opposite of design. In analysis, there is a building already erected on site. We know the dimensions of that building, we know the property of concrete and steel, and we know the area of steel reinforcement, everything that has been used, and we are checking what is the resistance capacity of that building and whether the reinforcement that I have used it is of required capacity or not. So simply saying, analysis check whether the design and detailing given to a structure is enough to resist the load and the moment acting on the structure or not. Okay, so we do design first and then we analyze, when then we do the analysis to cross check the design, we can say that. Okay, now I will just move to that doubt that someone was asking. There was someone who was asking some doubt, right? You can just type in the chat box right now, or you can unmute now. We'll discuss. So if you are getting confused between design and analysis, just don't get confused. Design is the first thing, and analysis is a cross check of design, we can say. There is some connection problems, that why just right now for some seconds the screen went off. Is someone having any doubt in this part? Someone unmuted and was trying to say something. If not, we'll continue then. Okay. So I was, as I was saying, uh, if we know what load is acting on our structure, we design that structure for the dimension and the material requirement. And once the design is done, once the structure is erected, we do the analysis just to check whether the design was done properly or not. Or if we don't know who has done the design and we are asked to check the structure whether it is proper or not, we do the analysis. Okay. Now, to achieve the three basic aim of design, that is safety, serviceability, and economy, there are different design methods that has been proposed. And these design methods are working stress method, which is also known as modular ratio method, ultimate load method, or we can say load factor method, and limit state method. Okay, all methods have one thing in common, that is to ensure that the resistance offered by the design structure should be more than the load acting on the structure. Okay, so the resistance that my structure is offering should be more than the load acting on the structure, so that my structure won't collapse under loading. Okay, so let's see what is the difference between these three methods. Okay, so first is the working stress method. Okay, so it is close to about 100 years old, and the method is based on linear elastic theory or classical elastic theory. Now, what we mean by linear elastic theory, we mean assuming that we are assuming both concrete and steel to behave elastically under service load. Okay, so that is the basis of linear elastic theory. Both materials are behaving elastically under the service load. So in this method, it is assumed that the structural material behaves elastically, and due to working load, the stresses are within the elastic limit. Okay. So design for based on working stress method ensures that stresses are developed within the working load within a permissible limit using a safety factor. So you can see here the definition that we have written: stress developed due to working load without any factor is less than the allowable stress or permissible stress with safety factor. So this is the equation that we are talking. So right in the last slide, we saw two terms, load and resistance. So here what we are doing, we are not applying any factor on load. Load we are taking as service load only, the working load, without any factor. But on the resistance that is offered by the building, we are applying a safety factor. Okay. So we can see in this equation, the safety factor is applied on the resistance that is offered by the building. So it's like we are decreasing the resistance offered by the building so that we can ensure that the load that is acting, it will still be lower than the resistance offered by the building. Okay. So in this method, you can see there is no serviceability that is considered. So that's why this method is less economic, since it is very old method. And it is a very simple method since we are applying factor of safety on only one side. Okay. And it doesn't distinguish between different load types. Okay. So that's why it is also less economical considered to other methods. Then the second one is ultimate load method. So this method is also known as plastics design, as it takes ultimate load into account. Now what we mean by ultimate load, so ultimate load is obtained by enhancing the service load by some factor referred to as load factor. So again, if we see, there are two terms, load and resistance. So in ultimate load method, what we are doing, we are increasing the load that is acting on the structure by multiplying it with some loading factors. So you can see here, ultimate load is the working load or the service load times the loading factor, and this increased load should be less than the strength of the structure. So the strength that we have provided to the structure should be more than the strength required to carry the ultimate load. So that is the basis of ultimate load method. We are applying factor of safety on load rather than resistance. Okay. So factored load are considered for different loading type that was not considered in a working stress method. And going till ultimate load will provide us more economical design, but concrete, which was assumed to take no tensile load, may show crack at higher load range. So here, since we are going to such a high load level, we are multiplying some loading factor on the load and then we are designing, there can be cracking issues in the concrete that can come up, and thus there can be some serviceability issues in the design. So both these methods, they are applying factor of safety on different parts. Working stress method was applying safety factor on the resistance part, while ultimate load method was applying safety factor on the load part. But both of them are still not taking serviceability or the cracking or the deflection in the composite material into account. And that's why we have limit state method, which is the most modern and followed practice. Okay. So it is more advanced than any other traditional design philosophies. And in ultimate working stress method, calculation was done based on ultimate load, working load. In ultimate load method, calculation was done on ultimate load. But in limit state method, we use ultimate load for safety and working load for serviceability. So we are taking both safety and serviceability into account. Okay, how? So there are two parts of limit state method. This one part is known as limit state method for safety, and one is known as limit state for serviceability. So when we design for safety, we use ultimate load into design so that my structure is safe against worst loading combination possible on the design on the structure. And for serviceability, to check for cracking or deflection, we take the service load into action, and we check whether my structure is performing satisfactory at the service load condition or not, so that the people who are using the structure are in comfort. Okay. So that's how we take both service condition and ultimate condition into design in limit state method. Now that we have discussed limit state method, let's understand what these partial safety factors are, and that and what all these probabilities and everything mean in design. So if you see in reality, the material strength and load, they can vary. They are not very fixed values, and there can be some distribution of load that is acting, like not always a fixed load will act on a structure, or not always a fixed strength is there of a material. It can show some variation. So to ensure safety in design, we treat this load and strength as a variable, and we use statistical tool like normal distribution to account for the variability. So if you see in the first graph on the left, it shows the basic bell curve, where most value cluster around mean. So you can see around mean there are higher proportions of value, and fewer values lies on the extreme. So this is known as normal distribution, which typically represents a loading condition on a structure. Okay. And in the second part, in the second graph, we see the how this normal distribution applies to design. So for strength, we don't use the average value. We use a value mean minus 1.65 times the standard deviation from mean. Okay, so this is the strength that we consider of our structure, of our RC structure. We consider this is the strength. Okay, that and this value ensures that and this value represents the characteristic strength of my structure, ensuring that 95% of the sample will exceed this. Okay, so more than 95% of the cases will exceed this line, that is ensured by taking this value as strength. And for load, for design, we take mean plus 1.65 times standard deviation as the loading acting on the building, so that we can take into account if there are some extra loads also that are acting on the building. So for while designing, we consider this load as for design, and while checking, we ensure that this our structure is meeting at least the strength level. Okay, so this approach is what justifies the partial safety factor in limit state method. It's all about designing for uncertainties that is commonly possible in real life. Now, in load, when we talk about extreme condition, we mean to say considering all types of loading that can act on a structure. So there can be different types of load that can act on a structure. There are dead loads, there are live loads, there are wind loads, and there are earthquake load. Now, how these load combine? So that is given to us by load combination. So load combination is a set of various loading conditions that are acting together in a structure, which ensures that the structure has required safety and economy in design. So you see this table. This table is taken from IS 456, and this table shows the value of different loading factor for different types of load. Okay, so we have dead load, imposed load, that is live load, and wind load. And there are two types of design check that we do. So for limit state of collapse, where we are using ultimate loading condition, we are concerned with ensuring that the structure doesn't fail. So we have higher safety factors applied to loads. So if you see, if there is dead load and imposed load, we apply these loads by a factor of 1.5. uh, okay, for dead load plus wind load, we either multiply both of them by 1.5, or we use 1.9 for dead load and 1.5 for wind load in case overturning is more critical in the structure. And these comments you can see here, at the down it is given why certain the types of factors are taken instead of common factor. And when we are taking all three loads into consideration, we multiply them by 1.2. Okay, in case of collapse. And in case of limit state of serviceability, it is more about ensuring comfort and durability, so lower load factors are used. So for dead load, live load, and imposed load, it is mostly taken as one. Safety factor is taken as one. However, for long term effect, sometimes we reduce the safety factor to zero point 0.8 also, to reflect a realistic usage of the structure. Okay, so this is how loading factors are taken into account. However, such factors are not same everywhere. So if you see how ACI codes takes these factors into account, so in ACI code, strength reduction factors or the loading factor or the strength reduction factor, they vary based on the design. So if you're designing for bending, they take a different set of reduction factor. If you are preparing for shear, different sets of factors are there, and if you are preparing for axial, different sets of factor are there. Okay, so unlike IS code, which takes a similar set of factors for any type of loading condition, ACI codes takes different sets of factor for different loading condition. And they also account for higher safety for live load and lower safety for dead loads. Why? Because they think like ACI code has a the philosophy that dead loads won't show much variation. However, live load can show much variation. So that's why they take more safety factor for live load and less safety factor for dead loads. So you can see 1.2 for dead load, 1.6 for live load. Unlike our case in IS design where we see take generally 1.5 for both dead load and live load. So these are some of the changes that are there in different codal provisions. Okay. Now, based on this part, just try to answer these questions. And in the meantime, if you have any doubts, you can ask. I hope that query that was posted on discussion forum would got cleared with this I ACI and IS code comparison. Okay, just try to answer these three questions. That's their basis of design. Like they consider that different types of low members require different types of loading factors, safety factors. So it is just their base of design. They don't consider same factor requirement for different types of loading. So like I can't directly answer why it is happening, but it is just how they have built up their code. Like for load, we can say we are using same safety for both dead load and live load. Now, what are these safety factors? These factors are taken into account so that we can consider the distribution. Like, suppose 100 kg dead load is present on the structure, it can vary from 75 to 150 kg. So, to just take that variation into account, we have loading safety factors in the picture. Now, IS code, it is taking 1.5 for both dead load and live load, but ACI code says that dead load should not show much variation. Live load is something that will show much variation. So that's why we take 1.2 for dead load and 1.6 for live load. Similar thinking might have been there for the uh, this strength factor also. Okay. So if you see the range, they think that more safety factors are required in shear and axial design rather than in flexure design. So that's why they have defined different sets, different ranges. Okay. and it also comes based on how their design codes are formulated, whether their design codes are more oriented towards ductile failure. If the design is more oriented towards resisting ductile failure, then they will apply less safety factors for flexure, and more safety factor for shear and axial, because the design was not primarily oriented for shear and axial failures. So that can also be one of the reasons why safety factors are different for different types of failure condition. I hope you got a little clarity about this. Okay, so let's see the answers to these three questions. Okay, first question: which design philosophy ensures a uniform margin of safety for all limit state considered? So we know the answer for this right now. We have discussed it is the limit state method. So in limit state method, we are ensuring there is a margin of safety considered for both ultimate condition and serviceability limit state using partial safety factors. Okay, so we are taking care of both serviceability and ultimate load, serviceability and collapse in limit state. Question number 8: in the working stress method, this factor of safety is applied to. So in working stress method, the factor of safety is applied only to the stress in the material, not to the load. Okay, so that's what we have seen earlier. The loading, we are assuming it as service load, and the stresses of the material we are decreasing, and we are ensuring that this decreased stress is also more than the load to ensure that this structure is safe. Or we can say only to the strength of the material, not the stress. Okay, so the strength of the material we are applying the factor of safety. Question number 9: in terms of safety philosophy, how do limit state method and ultimate load method differ? So So the correct answer will be B for this. So this we have also seen. Limit state method has a different separate philosophy for both serviceability and ultimate condition. Okay, so we have limit state of collapse and we have limit state of serviceability. So limit state of collapse deals with the ultimate load, and limit state of serviceability deals with the service load only. So at service load, it just ensures that there is no much cracking or deflection happening in the structure. That is the role of serviceability. And in limit state of collapse, the design ensures that at ultimate loading condition, the structure is safe. Okay, so that's how this is taking both serviceability and collapse into picture. However, in ultimate load method, we don't explicitly address serviceability. Okay, so when we design a structure for such a high loading condition, there can be cracking issues in the structure at normal conditions that is not addressed by the ultimate load method. Okay, so they doesn't explicitly address serviceability in their design. See, shear design is different from ductile design, and it is different from axial design. So when we talk about ductile failure, it is just the flexure part that is playing the role. While in shear, there are diagonal stresses that are generated, and in axial, there are compressive stresses that are dominating. So if you see a beam and a column, both are different types of elements. In beam, there are flexural strength. Flexural strength becomes important. However, in column, the axial capacity of column is important. So maybe in ACI code, the design is more oriented towards ductile failure. That's why they have imposed less factor of safety in ductile and more factor of safety is for shear and axial. It is not excluding, but it is more oriented for ductile. Are these three questions clear? Any doubts in these three questions? 7, 8, and 9. Just answer these two more questions. So these will be the last questions of today's session. Very basic questions just to check whether you understood the different design methods or not. Okay, so your answers are correct. Question number 10. Which of the following best compares the working stress method and limit state method? So the correct answer is C. Okay, so in limit state method, we are using different partial safety factors for different limit states. For the limit state of collapse, there are different factors that we have seen in this table, and for serviceability, there are different factors that we are taking. So this makes the design more refined and more realistic. While in ultimate working stress method, we are taking only one type of safety factor, that is for strength. Okay, and we are not concerned with the serviceability. We are just concerned with the collapse. Okay. Question number 11. In limit state design, partial safety factors differ for material and for load primarily because the answer will be B. Load and material uncertainties are independent and must be addressed separately. So if you see, partial safety factor differ to account for distinct uncertainties in load and material behavior. Like loading can have different types of uncertainties, the material behavior has different types of uncertainties, and limit state method treats both of them separately. So when we see this, okay, how we write, okay, so this is load, we are multiplying it by different safety factor, and this is resistance, we are reducing it by different service factor. Okay, so both these service factors are different. This is related to the variability in loading, and this factor is based on the variability in the resistance offered by the material, and that's why they are independent. So the load should be less than the resistance. That is the base end aim of the design. Okay. So this was all for today's session. Like this was just an introduction to the course, more towards the history, the need of reinforced concrete, and what are the objectives of design, why we need code, how design differ from analysis, what are the different design methods. That's all we have discussed in this session. Okay, from the coming week we will have more of questions than theory. Okay, because now assignments will also, I will also try to discuss the assignment question also, so that if anyone has any doubts they can address, I can address them. And I will have more questions because there will be more depth understanding about the concepts. Okay, so if anyone has any doubt regarding the week 1 content, still you can ask me now. Any doubts regarding week 1 assignment? So like I can't right now discuss the answers to the assignment question because I guess the submission is pending right now. But after submission next week we'll discuss the we will have a recap of assignment number 1. Right now you can just ask if you have any query in any questions there also.
Hello. So, uh,
Yes.
yeah, actually, it's regarding one of the mathematical model that was shown for concrete.
Which
Uh,
mathematical model in my slide?
uh, yeah, it was there here also, and as well as in the lecture also.
uh,
So
can
we are using
can you just brief a little more on which model you are talking? This
it's a normal distribution. Yeah.
just don't
It's,
take it as a mathematical model. Just see, I will tell you in very simple term. When we talk about load acting on a material or the strength of a material, these are not very fixed value. They can show some deviation. And this normal distribution and all, this is the simplest way to represent deviation. So suppose like in laboratory we prepare concrete. Okay, I have prepared concrete to achieve 25 MPa strength. I have prepared 10 number of concrete samples. Okay. And then I do compression testing of those 10 samples after 28 days. Okay. What I will observe, I won't get 25 MPa in all the concretes. When some concrete will show 25, some will show 28, some will show 22, some will show 23. So this is the representation of what is the distribution of the strength of my mixture or the capacity of my mixture. Okay, so this is just how we represent that. Generally if you will test like hundreds of samples of same batch, it will show a normal distribution. Most of the value will be around the mean of what you designed. So suppose using IS 456 and IS 10262, you followed the mixture proportion and you casted M25. So most of the strength will be around M25 MPa, but there will be cases which is deviating from 25 MPa also because of the material variability or the material variability in different batches that you have poured in. So this is just that simple representation of variability that can come. Don't get confused with the values. It is just the representation of distribution of values. Was I able to clear a little bit?
yeah, like actually, I had a doubt in the formula. I just went a bit more in depth in this
Okay, which
uh,
what is the
normal distribution. So there was a formula for variation. The variance was equal to square root of n minus. Uh,
that variation is known as standard deviation. Okay, so I will just write that equation here. So how we calculate mean? Can you tell me? So mean is sum of all values divided by number of values. Am I right?
like regarding the mathematical model.
Yeah, that is regarding math. I am clearing that all, that only the variation thing that you are saying, na?
Yeah.
Can you tell
So
me?
like, why should we? Yeah.
So can you tell me
Yeah.
whether I have written the mean formula correctly or not?
The model. Yes.
Okay. Now, how to calculate variation? Variation is, suppose I have 10 data values. What, how
Mm-hmm.
much they are deviating from mean? That is known as variation. Okay. So that's
Yeah.
why
Yes.
the formula that you will see for variance, it will be square root of the value minus mean upon so summation of square root of this divided by n minus 1. Okay, so this is how variation is calculated. This is just a mathematical representation, like how we calculate standard deviation. So that is just variation of all the values from mean. Okay. And in this figure that you see 34.1, 16.13.6, it is just representing how many values. Like suppose you have 100 data points. So 68 data points will lie within one standard deviation. Then 68 plus 14, then almost 95% of samples will lie in this bracket, mean minus 2 standard deviation into from mean plus 2 standard deviation. So this is just a representation, like you need to collect some data and try it out, then you will get more clarity. But just don't get confused of this variation formula.